Hello, this is Dr. AJ Kumar, PhD, and we're doing information theory again. Alright, and this one is called the chain rule of joint entropy, and it's Cover and Thomas, section 2.2. I don't like lecturing straight out of a book, but Cover and Thomas is a really good book, and information theory is such a interconnected topic that it's very difficult to approach linearly. Probability theory is kind of the same way, statistics same way. Um, and Cover and Thomas does a pretty good job of sort of presenting it from in a linear way, which is very difficult. Anyway, so first topic is just remind you of some facts about expectation. Hopefully you're familiar with this from probability theory. So x, big X, so this is annoying. A lowercase x is an element of the alphabet curly x. So x is a random variable whose alphabet is curly x, and that means that it's a discrete random variable, so it can have one of the values in big curly X. It has probability distribution pi. And then you have some other function f, which is just a real valued function. This should be curly x. Curly x to r. The expectation of f, which is written using this double E symbol, expectation of f is the sum over all members of the alphabet of the probability times f. So it's just a weighted sum according to the probability. And if you take the expectation of the variable x itself, that gives you the mean or the average. Properties, so the expectation is a linear operator. Now, just because it's a sum, so expectation of c times c is some constant times the function f is c times the expectation of f. E, the expectation of the sum of two functions is the sum of the expectations, and you just get that directly from properties of arithmetic. All right, example, this is the main example in information theory, is the entropy. So LB, that's my abbreviation, means binary logarithm, log base 2. So I'm not very good with my notation, but the entropy of x is the expectation of this function x, which goes to the minus the logarithm of the probability of x. Or another notational way to write that is minus the expectation of the logarithm of the probability, which I'll just remind you again is minus the sum of the probability times the log of the probability. And do not forget that minus sign, it's really important. Alright, so properties. First of all, it's always non-negative. And the reason is because the logarithm, let me switch to a brush. Really? Let me switch to, let me put the microphone down. So the logarithm, let me just draw some axes. So here is 1, here is 0. The logarithm has a curve, kind of goes off to negative infinity, kind of looks like that. And so between 0 and 1, the logarithm is negative. Well, probabilities are always between 0 and 1. So logarithm of the probability will always be negative times probability, which will be between 0 and 1. So everything inside this sum, this will be negative, but you put a minus sign here. So the entropy is always positive or 0. It is only 0 when pi is a guaranteed distribution. I did another video going over this, but basically if there's some event in the alphabet where the probability of that event is 1 and the probability of every other event is 0, entropy is another word for uncertainty. So that distribution has no uncertainty. The entropy is maximized the uncertainty is maximized on a uniform distribution. So it matches what you should expect from entropy. And today we're proving a different property of entropy, which is the chain rule of entropy, of joint entropy, and I'm going to explain what that is. So you have the entropy of a vector-valued random variable. So here we're talking about a variable with 2 dimensions. So it has an x component and a y component. And just the joint entropy is just the expectation. It's exactly what you would expect. I put a double sum here because that's convention, but you could just put a single sum over x, y in x comma y. Doesn't really matter. I'm not going to be super. I'm not going to be super specific with my notation. I just think that's a waste of time. If it's sometimes it's useful, but yeah, most of the time it's just you're being pedantic. Anyway, so I want to remind you about this thing called conditional probability. So here I meant to write this is x and this is y, and so this is discrete random variables. So these are some points, and within this pink region here, this is the probability that x is equal to x, and inside this little green region, this is the probability that y is equal to y, given that x is equal to x. So the product of these two is the probability of x comma y. So, right, it's just the probability of the logical conjunction. Probability of logical conjunction is always the product of the two. So the probability of x comma y is the probability of x times the probability of y given x. This is just the definition of conditional probability, which is you divide both sides of this equation by pi of x, and that's the definition of conditional probability. The logarithm of this probability, well, by the properties of logarithms, the product splits into a sum. So log of pi of xy is equal to log of pi of x plus log of pi of y given x. That's just applying the sum. And then therefore, well, if I take an expectation of both sides minus the expectation, and I forgot a bracket there, well, that's just by the linearity of the expectation. The expectation of a sum is the sum of the expectations minus expectation of log of p of x plus the expectation of log of p of y given, probability of y given x. Okay, well, this is just this expectation of the log of probability of x, that's just the uncertainty of x, or the entropy of x. This is called the conditional entropy of y given x, which is denoted h of y given x, which is the expectation of log of probability of y given x. And so we have this wonderful rule, which says that the uncertainty in a pair of random variables is the uncertainty in the first plus the uncertainty in the second given the first. Okay, that's called the chain rule of joint entropy, and that's all I wanted to talk about. It's literally just this. All right, thank you for watching. I'm Dr. AJ Kamor. Please keep watching this information theory playlist. We're going to get into a lot of really interesting stuff. We're going to talk about data compression. We're going to talk about, well, data compression is probably the most interesting. I'll probably, maybe at some point get to thermodynamics. A lot of really interesting stuff going on in information theory. It's one of the richest topics in mathematics, and it's a shame that it isn't taught to everybody. It's very beautiful, very simple. You kind of, the only annoying thing, I mean, probability, you have all this kind of notational annoyance, but otherwise it's a pretty nice theory. Anyway, thank you for watching.